Hello and welcome back. Let's start with examining the whys as usual. To give an idea why testing is important, I'm going to mention a number of real-world examples. So why is software testing important? Our first example will be about a software update for a smart thermostat produced by a company called Nest, which is actually owned by Google. And that software update went wrong and literally left users in the cold. When the software update went wrong, it forced the device's batteries to drain out, which led to a drop in the temperature. Consequently, the customers were unable to heat their homes or use any amenities. In August 2015, HSBC failed to process about 275,000 in individual payments that left many people without pay before a long bank holiday weekend. This occurred due to a major failure within the bank's electronic payment system for its business banking users. Again, in 2015, a programmable pump from a company called CareFusion was recalled over a software error that caused the pump designed to automatically deliver medicine and fluids to hospital patients to delay its infusion. The consequences can range from medicine being withheld at critical points or accidental overdosing and can be deadly. So software now is important to our finances, it is important to our infrastructure, and it's important to our lives. And we rely on software testing to help us get it right. To make sure software performs as expected, we have to do two things well. Those are verification and validation. We would like to make sure that software is meeting the user's needs. So verification, this asks a question, are we building the software right? We assume that we have some requirements formalized as a specification, and our goal is to verify that the software conforms to the requirements. Validation, however, asks a very different question. Are we building the right product? At the end and throughout, we would like to make sure that what we have built is what we should have built. First, we understand and validate the software requirements, whether or not we write them down. That is to stress that in order to build tests for a piece of software, we first have to understand what it does and what it should do. We further can apply verification and validation throughout the development cycle. For instance, we can allow other people to look over the code we write, design discussions to make sure that the code that we're going to build is going to meet its performance and security requirements. We can perform static analysis that can check our program for well-formatness. Does it have any integer overflows or null pointer references? Such things. Testing, which is the focus of today's lesson, and runtime verification, which helps to shut down and inspect the software in case we see any anomalous behavior. Testing lets you study a piece of code to see whether it meets the requirements and whether it works correctly under all circumstances. Other good things that the testing provides it is virtually the only defect detection technique that can check the whole system. It can assess some kinds of system behaviors, such as performance. Oftentimes, it's just necessary for the customer to accept the system when you build something for, say, the government. And finally, testing is a reasonably good way of documenting expected system behavior. So a bug is a flaw in a program that causes it to produce an incorrect result or to behave unexpectedly. However, it's not always worth your effort to try to remove every bug. Let's see some of the reasons why software developers sometimes don't remove all errors from their applications. Finding the first few bugs in a newly written piece of software is relatively easy and therefore cheap. However, after a few months of testing, finding bugs may become prohibitively difficult. In a fair world, software is released when it's ready. However, in the real world, we have deadlines, so you might be forced to release your software if most high-profile bugs have been squashed, and the remaining bugs are not too bad. Sometimes fixing a bug might force you into other changes in code. For instance, fixing a file format for your application may force users to convert all of their files. You also don't want to release patches too often. Users won't like you if you release new bug fixes every 3 days. As a rule of thumb, you would fix security issues immediately, serious flaws monthly, minor flaws 2 times a year, and nice to have new features yearly. Sometimes users rely on a particular bug to do something sneaky that you didn't intend them to do. They won't thank you if you remove their favorite feature, even if it started out as a bug. Over time, some features may become less useful. Eventually, they may even go away entirely. For example, most developers won't fix bugs in floppy, CD, or DVD drive controllers these days. Sometimes users think a feature is a bug. So this is really a problem of user training. So more detailed documentation, updates on user interface, or grouping logical features together might be a solution. But there is a more fundamental reason. Imagine that you are looking at the wall, and the wall represents all the possible behaviors of the system. But all you can see is through these little holes that are on the wall here. And you have to kind of look through there and try to inspect what's going on inside the wall. Let's assume that the system's state space is a big cloud of possible values that the system is in. When we make mistakes, when programmers make bugs, they make them uniformly across their different places. So when we do testing, we do these point checks of the software, and these star points aren't necessarily telling us about the points nearby. So if we don't exactly hit a bug, we won't know that there's some buggy behavior very, very close to the value that we chose. This justifies that there's no basis for extrapolating from seen cases to unseen ones. So this is why the testing is inherently hard. It even made Edgar Dijkstra to say that testing can only show the presence of errors, not their absence. As you might guess, hitting a bug accidentally doesn't necessarily tell you that you have actually got rid of all of the bugs in your program. Let us look a little bit more closely on the different levels of software testing. That is unit, component, and system testing. Unit testing is the process of testing program components, such as methods or object classes. That is individual unit in your program. When you're testing object classes, you should design your test to provide coverage of all of the features of the object, and call these routines with different input parameters. This means that you should ideally test all operations associated with the object, set and check the value of all attributes associated with the object, and put the object into all possible states. This means that you should simulate all events that cause a state change. Testing composite components should focus on showing that the component interface behaves according to its specification. You can assume that unit tests on the individual components within the component have been completed. The test cases are not applied to the individual components, but rather to the interfaces of the composite component created by combining these components. This means we have to call the interface of the composite component in order to test it. Some general guidelines for interface testing are examining the code to be tested and explicitly listing each call to the external component. Design a set of tests in which the values of the parameters to the external components are at the extreme ends of their ranges. These extreme values are most likely to reveal interface inconsistencies. Where pointers are passed across an interface, you should always test the interface with null pointer parameters. Where a component is called through a procedural interface, you should design tests that deliberately cause the component to fail. Differing failure assumptions are one of the most common specification misunderstandings. You should also use stress testing and message passing systems. This means that you should design tests that generate many more messages that are likely to occur in practice. This is an effective way of revealing timing problems. When several components interact through shared memory, you should design tests that vary the order in which these components are activated. Those tests may reveal implicit assumptions made by the programmer about the order in which the shared data is produced and consumed. When you integrate components to create a system, you get emergent behavior. This may be planned emergent behavior which has to be tested, but sometimes the emergent behavior is unplanned and unwanted. Therefore, system testing should focus on testing the interactions between the components and objects that make up a system. Because of its focus on interactions, use case-based testing is an effective approach to system testing. Typically, each use case is implemented by several components or objects in the system. For most systems, it is difficult to know how much system testing is essential and when you should do stop testing. Exhaustive testing, where every possible program execution sequence is tested, is impossible. Testing, therefore, has to be based on a subset of possible test cases. Best practices, however, typically indicate that all system functions that are accessed through menus should be tested, as should be combinations of functions such as text formatting that are accessed through the same menu. Whenever user input is provided, all functions must be tested with both correct and incorrect inputs. Integration and regression testing, as opposed to previous types of testing, have to do more with development activities rather than software structure. Each time you write a chunk of code and use unit tests to verify that it works or seems to work, you end up integrating it into the existing codebase. Integration test verifies that the new method works and plays well with others. It checks that existing code calls the new method correctly, and then the new method can call other methods correctly. In regression testing, you test the program's entire functionality to see if anything changed when you added new code to the project. These tests look for ways the program may have regressed to a less useful version with missing or damaged features. Incremental integration and testing is fundamental to modern agile methods such as XP. The goal of acceptance testing is to determine whether the finished application meets the customer's requirements. Normally, a user or other customer representative sits down with the application and runs through all the use cases you identified during the requirements gathering phase to make sure everything works as advertised. Whenever possible, you should automate user unit testing. In automated unit testing, you make use of a test automation framework such as JUnit for Java or PyTest for Python to write and run your program tests. So what exactly is a software implementation of a test? We start with software under test. When we say software, we do not necessarily mean the entire finished software product. Quite the contrary, software under test means whatever part or subset of the program we have completed where we can exercise some behavior. This is some module or unit of the code, hence unit testing. To run a test against our software unit, we must provide it with the information on which to act, the input, or the test data. Note that we can generate test data based on a profile we constructed of how we think the user will act, based on probability or even some user status, or we can attack the code with some data that often causes errors. For each of these user inputs, we run the software given the user data, setting up the software to be in the right state for the software test data to make sense. Once the software is given the test data, we watch the output, the behavior of the program given that output. The question is, has the software provided the correct result? To figure this out, there is an oracle. Traditionally, the oracle is the developer or tester who runs the tests. However, currently more and more automated oracles emerge. Frameworks such as PyUnit or JUnit allow you to quickly run hundreds or thousands of tests, check their results automatically, and present them visually. The test data, software output, and the expected output are all supplied to the oracle, so it is able to decide whether the program performs correctly. Test data and expected output together make the test cases. This figure represents an abstract model of the traditional testing process. Test cases are specifications of the inputs to the test and the expected output from the system, the test results, plus a statement of what is being tested. Test data are the inputs that have been devised to test a system. Test data can sometimes be generated automatically, but automatic test case generation is impossible, as people who understand what the system is supposed to do must be involved to specify the expected test results. However, test execution can be automated. The expected results are automatically compared with the predicted results, so there is no need for a person to look for errors and anomalies in the test run.